Greetings, let us embark on a thoughtful journey together. We journey far beyond our world, guided by the powerful vision of the James Webb Space Telescope, or JWST, launched just a few years ago. This observatory is already reshaping our understanding of the cosmos. Today, Friday, April 11, 2025, we will explore some of the most significant findings reported recently, perhaps within the last year. More importantly, we will practice thinking critically about them. We will ask, what do these discoveries truly mean? What questions do they raise? And how do they challenge what we thought we knew? Let us proceed slowly and with curiosity. Section 1. The Impossible Early Universe. One of JWST's primary missions is to look back towards the dawn of time, to see the first stars and galaxies forming after the Big Bang, and it has delivered sights that are both spectacular and puzzling. Webb is consistently finding galaxies in the very early universe, sometimes appearing just 300 to 500 million years after the Big Bang itself. How do we know they are so old? It involves measuring redshift. Imagine the sound of an ambulance siren changing pitch as it moves away. Light from distant, receding objects does something similar. Its waves get stretched out, shifting towards the red end of the spectrum. The greater the redshift, the farther away, and the further back in time we are looking. JWST is finding objects with very high redshifts. But here is the puzzle that scientists are actively debating right now. In 2025, many of these earliest observed galaxies appear surprisingly massive, bright, and perhaps more structured than our standard cosmological model. The Lambda-CDM dark matter model predicts should be possible so early on. It is like finding large, well-built cities just a few years after the founding of a country. This leads us to ask fundamental questions. Does this mean our understanding of how quickly galaxies can assemble is incomplete? Did the first generation of stars form differently, perhaps much larger and burning out faster, seeding the universe with heavy elements sooner than expected? Or could there be issues with how we interpret the brightness and mass of these distant objects? Adding to this complex picture is the search for the seeds of supermassive black holes. We know these giants exist at the centers of most large galaxies today, including our own Milky Way. But how did they get so big, so fast? JWST is hunting for evidence of their origins in the early universe. Finding massive black holes already present in those first few 100 million years would add another significant challenge to our models of cosmic evolution. It is crucial to understand. Science thrives on such challenges. These surprising findings do not necessarily mean our core theories are wrong, but they highlight areas needing refinement or perhaps new physics. Extensive follow-up observations, especially detailed spectroscopy to confirm distances and analyze the chemical composition of these early galaxies, are underway. We must think critically. Are we seeing evidence that fundamentally changes cosmology? Or are we seeing the expected complexity that arises when we look at the universe with sharper vision? What alternative explanations exist? What specific data will help differentiate between possibilities? This is Science in Progress. Section 2. Decoding Alien Skies. Hopes and Hurdles. Let us now shift our focus from the edge of time to worlds orbiting other stars. Exoplanets. JWST possesses an extraordinary ability to sniff the atmospheres of these distant planets. Often, it uses the transit method. When a planet passes in front of its star, starlight shines through the edge of the planet's atmosphere. Different gas molecules absorb specific colors or wavelengths of light. By analyzing the starlight spectrum after it passes through the atmosphere, JWST can identify the chemical ingredients present. Recent studies, reported over the last year or so, have provided increasingly detailed atmospheric compositions for a range of exoplanets. We have seen confirmations of water vapor, H2O, carbon dioxide, CO2, and methane CH4 on gas giants and Neptune-sized worlds. Excitingly, Webb is also studying smaller, potentially rocky planets, including some within their star's habitable zone, the region where temperatures could allow liquid water to exist on the surface. Detections of molecules like CO2 or even water vapor in these smaller atmospheres are significant milestones. However, this is where critical thinking becomes absolutely essential. Finding water vapor in an atmosphere does not automatically mean lakes and oceans, let alone life. Venus has water vapor in its atmosphere, but its surface is scorching hot. The presence of a molecule must be interpreted within the context of the whole planet, its size, temperature, the type of star it orbits, and potential geological activity. What does detecting CO2 tell us? It might relate to volcanic activity or atmospheric loss, not necessarily biology. The search for biosignatures, signs of life, is even more complex. Scientists understand that single molecules are usually not sufficient proof. For decades, researchers have theorized that certain combinations, like oxygen and methane existing together in large amounts, might be suggestive, as these gases tend to destroy each other unless continuously replenished, potentially by life. However, non-biological processes might also create such combinations under specific planetary conditions. Recent discussions even involve searching for more complex molecules potentially linked to life. But identifying these unambiguously across interstellar space is incredibly challenging. We must ask, how do we avoid false positives? How can we be sure a detected signal is from biology and not geology, or atmospheric chemistry we don't fully understand yet, or even contamination from the star itself? Interpreting exoplanet atmospheres requires sophisticated computer models, but these models have uncertainties. JWST provides the raw data, the spectra, but turning that data into reliable conclusions about habitability, let alone life, is a careful, ongoing process filled with scientific debate. What level of evidence would truly satisfy the extraordinary claim of finding life elsewhere? Section 3. Witnessing birth, stars and planets forming. Beyond these headline areas, JWST continues to deliver breathtaking images and data from closer regions. Its infrared eyes pierce through dust clouds that obscure the view for other telescopes, revealing intricate details within stellar nurseries. Vast nebulae where stars are born. We are seeing jets from young stars, protoplanetary disks, the swirling gas and dust where planets form, with gaps and rings suggesting nascent planets, offering unprecedented clues about how systems like our own solar system came to be. Conclusion: the journey of understanding. As we stand in early 2025, the James Webb Space Telescope has already profoundly expanded our cosmic horizons. Yet, perhaps its greatest contribution is not just the answers it provides, but the depth and quality of the new questions it forces us to ask. The universe, as seen by Webb, appears more complex, perhaps evolving faster in its early stages, and chemically richer than we might have assumed. Interpreting Webb's data requires immense care, collaboration, and critical thinking. It reminds us that science is not about finding simple truths, but about building progressively better models to understand a complex reality. Constantly testing those models against observation. The journey with JWST is far from over. It is a continuous process of discovery, challenging our assumptions and expanding not just our knowledge, but our capacity for wonder and critical inquiry.